Alright, welcome to the marsh ecosystem. So marshes buffer storms, prevent shoreline erosion, and offer nesting sites for migratory waterbirds, and absorb excess nutrients at lower oxygen levels. Their saturated moist soil conditions and limited land give rise to soft stem vegetation, protecting against hurricanes by absorbing water. However, industrial development can remove marsh sponges, reducing fish populations by rising salinity, intensifying competition, and lowering carrying capacity. Without these sponges, marshes can't absorb pesticides and pollutants, leading to coastal dead zones. So here's some examples of food chains where algae convert solar energy into usable forms for upper-level trophic levels, aka consumers, where all food chains eventually lead to the marsh hawk, the apex predator. Notably, the algae are both producers and decomposers, meaning they conduct both photosynthesis and cellular respiration, since they live in water, making them a keystone species. Now you can see where these food chains fit on a larger scale, as well as the hierarchy of these organisms. A common trend here is that 10% of the previous trophic level's energy is transferred to the next, with detritus and woodcut mushrooms decomposing to 90%. If we arrange this on an energy pyramid, we can see that although the marsh hawk has the most predator-prey relationships, it receives the least amount of energy since it's at the uppermost trophic level. As energy is lost by heat, the decomposer recycles back into the environment. Most notable here is that algae produce oxygen by photosynthesizing, while plants filter water and offer a substrate for algae attachment, resulting in clear water and carbon cycling by removing excess nutrients and preventing eutrophication. Next, commensalism. Milkweed beetles have a unique adaptation that allows them to feed on milkweed, so the beetles gain protection from predators and sustenance, meaning they also have a predator-prey relationship. Finally, parasitism. Mosquitoes are a primary parasite in the marsh, as they increase disease transmission rates by feeding on the blood of the red-winged blackbird for sustenance. Here, the algae's photosynthesis provides nutrients for the marsh, while mosquito larvae consume these nutrients, increasing the mosquito population and influencing disease transmission rates. Next, great herons consume fall fish, affecting the availability of prey and consequently migration patterns for ducks. Last but not least, cattails and algae compete for abiotic factors like light and nutrients, shaping the amount, location, and structure of vegetation, as well as nutrient cycling. Now, the marsh hawk, the apex predator, gets the least amount of energy from sunlight, 0.01%, but has unidirectional predator-prey relationships across trophic levels 3 and 4, or the 2 trophic levels below it. For example, it preys on blackbirds, which consumes mosquitoes and milkweed beetles feeding on algae. This creates almost a mutualistic relationship where the hawk balances populations by preying on its consumers, aiding algae's oxygenation of marsh water via photosynthesis, and also maintaining the equilibrium of the ecosystem. And you can see how this ties into the carbon cycle here. The marsh hawk also preys on shorebirds, ribbon snakes, fallfish, and more on the food web. Other consumers also target these prey, but the hawk's ability to target a broad range of organisms gives it a competitive advantage for natural selection, meaning even though it's a quaternary consumer, it doesn't always get 0.01% of the sun's energy, since it draws from multiple trophic levels. Autotrophs such as algae convert CO2 to O2 through photosynthesis, establishing a photosynthesis respiration feedback loop that supports the marsh hawk. Carbon circulates through autotrophs during photosynthesis, later assimilated by marsh hawks as they indirectly consume primary producers. Additionally, decomposition and combustion release carbon back into the atmosphere or cycle it through detritus and organic matter. However, disruptions like industrial development drains the marsh's ability to absorb water and wind, reducing the available land and carrying capacity for fish and other aquatic organisms. As fish populations decline, the predation pressure on producers like algae and cattails decrease, increasing their population and their carbon capture, which indirectly affects the higher trophic levels like the marsh hawk. Cattail root nodules house nitrogen-fixing bacteria that convert atmospheric nitrogen to ammonia. Marsh hawks distribute nitrogen by consuming prey, spreading it across multiple trophic levels. Detritus and whitecaps also decompose organic nitrogen into ammonia. However, disruptions like reduced bacterial activity or excess fertilizer can disrupt plant growth, affecting marsh hawks' shelter and food availability, while excess nitrogen can cause eutrophication, affecting water quality. And this is where algae comes in. It all comes full circle. to how algae controls the water quality through the mutualistic relationship with freshwater clams. Thank you.